No. So good evening to everyone. So coming to today's session, as part of GATE 2026 Score Booster Series, today we are going to discuss about operating system related questions in connection with the NAT type as well as MSQ type. So before going to see that, I just want to showcase as per IIT Guwahati, it has been conducted previously 2 years like 2018 and 2010. And the weightage of this particular operating system subject is in 2010 it is 7 marks and 2018 you are having 8 marks. So by considering in and average in even in the 2026 also we can expect 8 marks. So this is what expected weightage, I can say expected weightage of operating system. Okay, expected weightage of operating system in 2026. So now let us start with the first question. So look at this question statement which is related to inter-process synchronization. Have a question statement, look at the question statement carefully. Consider the methods used by processes P1 and P2 for accessing their critical sections whenever needed as given below. The initial values of shared Boolean variables S1 and S2 are randomly assigned. So this is the code that is given to P1. This is what your P1, okay. This is what your P1 process and this is what your P2 process. So even though it is not given reminder section, we should assume that there is a reminder section here. Now check this one, which one of the following is achieved? Is it achieving mutual exclusion? Is it achieving progress, or else is it achieving bounded weighting, or else is it a strict alteration methodology? So this thing we have to check here. So this is MSQ. Sometimes S1 is 0 and S2 also 0. Sometimes S1 is 1 and S2 is 1. So this is called random assignment. Okay, this is called random assignment. Now first we are checking with this mutual exclusion statement. So recall what is the definition of mutual exclusion. Mutual exclusion defines that only one process can be part of the critical section at any point of time. Then how to check the mutual exclusion? So we can start execution of either one process or else we can start execution of both process, and we'll keep one process inside the critical section and then we can take preemption towards the next process and we'll check whether the next process is able to enter into critical section or not. So here this is what the entry section and this is what exit section, and similarly this is what your entry section and this is what your exit section. Now I can start execution of either P1 process or else P2 process. Let's say if I start with the P1, and among these four possibilities, random assignment of P1 and P2, random assignment of S1 and S2, among these two, what I am considering? I am considering the first combination. What is the first combination? S1 is equals to 1 and S2 is equals to 0. I am taking this combination to check all the requirements. So now S1 is 1 and S2 is 0. So if you verify, S1 is 1 and S2 is 0. 1 is equals to 0. Is the condition is true? No, right? It is false. As this condition is false, P1 is able to skip the while loop and it can enter into critical section. Now P1 is in critical section. While P1 is in critical section, if I take preemption towards the P2. Now for P2 also the same assignment I have to take. S1 is 1, S2 is 0, 1 not equals to 0, condition is true, right? So as this condition is true, P2 is stuck in the while loop because we are having semicolon here. So now, among these two processes, how many processes can be part of the critical section at the same time? Only P1 process. Okay. So which means, what is the definition of mutual exclusion? At any point of time, only one process can be part of the critical section. So here among this P1 and P2, you can see that only P1 can be part of the critical section. So which means this mutual exclusion is achieved, or else you can say ensured, or else satisfied, right? Achieved, or else ensured, or else satisfied, right? Satisfied. So these are all guaranteed. Okay, these are all synonyms. You can say that these are all respective synonyms for saying that these are all you can say that interchangeable terms, right? So interchangeable terms. So guaranteed, or else achieved, or else ensured, or else satisfied. So these are all called interchangeable terms. Okay. So in this case of P1 and P2 codes, if you consider, mutual exclusion is ensured here, means it is achieved. So option A is the answer for this question. Then check with the progress. Check with the progress. So verify, if you check the first two possibilities, these two possibilities are in the favor of which process? These two possibilities are in the favor of P1 process. And the next two possibilities are in the favor of P2 process, correct? First two possibilities are in the favor of P1 and the next two possibilities are in the favor of P2. So as we have taken this one, so we can see that P1 is able to enter into critical section, fine. But how to check the progress? So what is the definition of progress? When critical section is free, if process Pj is trying to enter into critical section, then process Pi, which is working outside of the critical section, should not block process Pj from entering into critical section. This is what your progress description. Now how to check the progress? The definition itself, if you can see, we are ensuring that the critical section is free, so nobody is there in the critical section. Okay, assuming that nobody is there in the critical section, assuming that nobody is there in the critical section, critical section is free now, and with this possibility, S1 is equals to 1 and S2 is equals to 0, with this possibility, who is able to enter into critical section? P1. But what this P1 is doing, this P1 is working, right? This P1 is working outside of the critical section. It means it is working in the remainder section. So while P1 is in remainder section, verify again the definition of progress. Critical section is free, one process is working outside of the critical section. Then P2, which is trying to enter into critical section with what values of S1 and S2? With S1 value is 1 and S2 value is 0. It is trying to enter. By the time critical section is free and P1 is working outside of the critical section, then is the P2 is able to enter into critical section? Verify. 1 not equals to 0, condition is true. So that P2 is unable to enter into critical section. It is stuck in the while loop, means it is stuck in the entry section. So critical section is free. One process is working outside of the critical section. Another process is tried to enter into critical section but got failed, not able to enter into critical section. Which means the process which is working outside of the critical section is blocking P2 from entering into critical section. But according to the definition of progress, a process which is working outside of the critical section should not block other process which is trying to enter into critical section. But here P1, by sitting in the remainder section, it is blocking the P2 from entering into critical section. So that's why we can say progress is not achieved, progress is dissatisfied, progress is violated, progress is not ensured, right? Then we are checking with the bounded waiting, right? So coming to the bounded waiting, what is the definition of bounded waiting? Please verify. What is the definition of bounded waiting? Bounded waiting definition is a process is not allowed to enter into critical section repeatedly. Okay, a process is not allowed to enter into critical section repeatedly, or else what we can say, when critical section is free, if process Pj made a request to enter into critical section, then before that request is granted, there should be a bound for another process Pi from entering into critical section, right? From entering into critical section, there should be a bound for another process Pi from entering into critical section. Means while a process is trying to enter into critical section, for another process there should be some bound. It means a process is not allowed to enter into critical section repeatedly. So for that, what we should do, we know that in order to check the bounded waiting, our concentration must be on exit sections, right? So assuming that with S1 is equals to 1 and S2 is equals to 0, who can enter into critical section? Verify. Who can enter into critical section? P1, right? S1 is 1, S2 is 0, 1 is equals to 0, condition is obviously false, so that P1 is entered into critical section. Now this P1, while it is coming out of the critical section, it is executing the exit section. What it is doing, whatever the current value of S2, it is loading into S1. What is the current value of S2? The current value of S2 is 0. Now what it is doing, it is loading that 0 into S1. So before this assignment, S1 is 1 and S2 is 0. Now what happens? The current value of S2, that is 0, you are loading into S1, which means your S1 value is 0, right? And S2 value is 0. Then while you are coming out of the critical section, you are making S1 value is 0, and again if you tried to enter into critical section, then for the second iteration, what is the value of S1? 0. And what is the value of S2? 0. So 0 is equals to 0, condition is true. As the condition is true, then P1 is stuck in the while loop. It means a process is not able to enter into critical section repeatedly, right? A process is not able to enter into critical section repeatedly, and that too, exit sections are different here if you check, right? So then obviously, what is the scenario? We can say that P2 is having bounded waiting, not unbounded waiting. So one time P1 is able to enter into critical section, another time P2 is able to enter into critical section. Among the P1 and P2, no process is able to enter into critical section repeatedly. So that is why we can say bounded waiting is satisfied here, right? So with S1 is 0 and S2 is also 0, who can enter into critical section? P2. Now S1 value is 0 and S2 value also 0. 0 not equals to 0, condition is false, so that P2 while loop condition is getting false, so that P2 is entering into critical section. Now while this P2 is coming out of the critical section, what it is doing? Not of S1, what is the S1? 0. Not of 0, what is that? 1. So that 1, this time you are saving into S2. So for the second iteration, what is the S2 value? 1. And what is the S1 value? 0. 0 not equals to 1, condition is true. So that P2 is stuck in here. Are you following me? So which means P2 is not able to enter into critical section repeatedly, as well as P1 is also not able to enter into critical section repeatedly. Then what happens? Both processes are having bounded waiting together. That's why we can say bounded waiting is satisfied here. I hope you are following this explanation. Then coming to option D, strict alteration. Is it a strict alteration or not? With this assignment, S1 is 1 and S2 is 0. With this assignment, who can enter into critical section first? Verify. P1. P1 can enter into critical section first. Is P2 is able to enter into critical section? No. So what does it mean? With this combination, as P2 is having control to enter into critical section, always first the P1 only can enter into critical section, after that P2, and then again P1, and then again P2. But with this combination, P2 cannot enter into critical section first. So always you are going to have only one execution order here. What is that execution order? P1, P2, P1, P2, P2, P1, P2, like this it goes. But you never get an execution order of starts with P2. P2 never enter into critical section with this combination. So that is why we can say it is also following the strict alteration. So overall, the answer for this question is A, C and D. So this is the answer for this question. Okay, right. So let's move to the next question. I believe you are clear with the explanation of this question. Let's move to the next question. Yes. So this is another question. I can say this time it is NAT type question. What is the answer for this question? Please verify what is the answer for this question. If you are able to answer this question, what is the answer for this question? Please let me know. So people who are part of live session, can you please give me the key for this question? Right. So coming to the solution for this question, you are having 3 page frames and with no pages loaded to begin with. What does it mean? According to this line, we are applying pure demand paging concept. We are applying pure demand paging concept. So the meaning of pure demand paging is initially your memory is empty with 3 frames. Then the system first accesses 100 different pages in some order. 100 different pages. The question is clearly mentioned different pages. So as it is different pages, I can say 1, 2, 3, 4, 5, 6 like this. It goes up to 100. As these are all different pages, and so since everyone is different, I can say 100 page faults can occur here. By the time of this 100 in your memory, what are the pages you are having? You are having 98, you are having 99 and you are having 100. Then accesses the same 100 pages but now in the reverse order. In the reverse order, in the sense, again it starts with 100, 99, 98 and so on, 97 and so on, 1. So in the reverse order, if you access, for these 3 frames, as these are already part of the memory, you are having hits. Then from 97 to 1, as these are all again different pages, you can have 97 number of page faults. So overall, your FIFO for this kind of question, how many number of page faults it can generate? 197 page faults it can generate. See, for the first 2 questions, whatever the question, this question and the previous question, this question, both are from your 2010, which is previous questions that are given by your IIT Guwahati. But what I have done, I have changed those question statements. I have done some changes in those question statements. Okay, right. So this is 197 is the answer for this question. I hope you are following this. Okay, so let's move to the next question. Yeah, so look at this question statement and give me the answer. If you are able to answer this question, let me know what is the answer for this question. Right. So this is the question which is related to demand paging concept. The average memory access time in the system is given 20 units. Let's say memory access time is given 20 units. If the corresponding memory page is available in the memory, right? So memory access in the system is 20 units if the corresponding memory page is available in the main memory. It means when there is a hit, then 40 units if the memory access causes the page fault. What does it mean? The page fault service time is given as 40 units. Okay. So it has been experimentally measured that the average time taken for a memory access in the process is 80 units. See, generally consider this question statement as a hypothetical. Okay. So generally it is effective memory access time, right? So effective memory access time is given as 80 units here. Then it is speaking about what is the page fault rate. So you know that in the demand paging, effective memory access time is equals to, what is that? P into S plus 1 minus P into M. Then what is the P? We need to find out. This is 80. Okay. P into S we need to find out. So I can say this is 40 into P. 1 minus P into, what is that M? It is 20. Then 80 is equals to 40P plus 20 minus, what is this? 20P, correct? Then 80 and 20 it comes, then it is 60. 40P minus 20P, what is that? 20P. Then if I want to calculate P, then it is coming to 60 by 20, which is 3. Actually, the page fault rate will not be like this, right? So generally we used to have one page fault per references or something we used to have, but this is hypothetical case. Okay, so don't think much practical. Hypothetical case. I just given this question in a hypothetical manner, just for giving a practice on this formula. It's not based on, you know, conceptual. Generally we used to have that page fault rate is in terms of some percentage, 90%, 80%, or means which is less than 1. So if you want me to solve that, then I can say this is going to be, if I take this is 10, effective memory access time is 10 units, then what is the value I am going to get if you check? What is the value I am going to get? So if it is 10 effective memory access time, then this is coming to 10. This is also coming to 10. And then what will happen? This is going to be somewhat negative value, right? So better you please consider with 80 units only. It's better always. Okay. So hypothetical case. Okay. Don't consider in practical case. So hypothetical case only I am considering here. So then you are getting this kind of answer. Okay. Please mind this hypothetical. Okay. Right. So let's move to the next question. So look at this question. What is the answer for this? A CPU scheduling algorithm determines an order for the execution of its scheduled processes. Give 4 processes to be scheduled on one processor. How many possible different schedules are there? So as the question, as per this line, you are having uniprocessor system. As per this line, it is a uniprocessor system. If it is uniprocessor system, how many number of processes can run at a time? Only one. right? Only one can run at a time. Only one can run at a time. Only one process can run at a time. Okay. Then how many processes you are having here? 4 processes. P1, P2, P3 and P4. So P1, how many possibilities are there? It can schedule either in first position, or else it can be scheduled on second position, or else it can be scheduled in third position, or else it can be scheduled in the last position. So P1 is having 4 possibilities. Then what about P3 or P2? Let's say if P1 have chosen first position, for example, if it is going to execute in the first time, I mean it is going to execute on the CPU in a first position, then P2 is having how many positions? How many combinations? 3 combinations. It can be executed among these 3. It can be executed either in the first position, or either in the second position, or either in the third position. Means you can say here. It means this P2 is having how many combinations? 3 combinations, 3 possibilities. Then if you choose only these 2, for example, if P1 have chosen the first position and P2 is having chosen second position, then P3 is having how many combinations? It can be executed in this position, I mean prior to P4 or after the P4. It means 2 possibilities. Then P4 is having only one position, that is going to be last. So overall, by considering this, how many combinations, how many possibilities, different schedules are there? In the sense 4 factorial. So that is a way how we can define this question, like how many possible different schedules are there? In the sense 4 factorial. So this is the way how you can answer this question. I hope you are clear with this. Okay, right. So let's move to the next question. So coming to this question, consider the following from the below data. How much average waiting time is deferred if we use round robin scheduling algorithm with the time quantum is equals to 2 compared to FCFS. So first, if you check with the FCFS, so what is the Gantt chart for this FCFS? At 0, AI is arrived with 3 execution time. So since it is alone process, we can hand over it, it gets executed up to 3 because FCFS is non-preemptive. By 3, who is coming? Only B is coming. B is coming with how much execution time? 6. So now who can go? Only B is available, so that's why B can go onto the CPU, gets executed up to 9. By 9, all the remaining processes are coming, like C is coming, D is coming, and E is also coming. So C is arrived with execution time of 4 units, D is arrived with execution time of 5 units, E is arrived with execution time of 2 units. Then among these 3, which process is arrived first? C. So that C will go onto the CPU, gets executed up to 13. By 13, you are having in the ready queue D with 5 execution time, E with the 2 execution time. So among these 2, who will go onto the CPU? Let's say D will go onto the CPU because D is entered first comparatively E. So now this is going to be executed up to 18, and by 18 you are having E process with 2 execution time. So since it is alone process, we can hand over it, it gets executed up to 20. Okay, up to 20. So this is what the Gantt chart for this FCFS. Then as the question is asking about average waiting time. So if I take completion time, A is completed by 3, B is completed by 9, C is completed by 13, D is completed by 18, and E is completed by 20. Then turnaround time. Completion time minus arrival time 3, 7, 9, 12, and again 12, right? Then waiting time. Turnaround time minus execution time. 3 minus 3, 0. 7 minus 6, 1. 9 minus 4, 5. 12 minus 5, 7. 12 minus 2, 10. Then average waiting time in the context of FCFS, if you calculate 10 plus 7, 17. 17 plus 5. 17 plus 5, 22. 22 plus 1, 23. So 23 by 5. So 4 point, right, 4.6 you can say. This is what FCFS case. Then coming to round robin. If you take round robin, this is what my ready queue and this is what my Gantt chart. First, which process arrived? A. Then from 0 to 2, A can be executed. Then by 2, who is coming? B. And with this execution, is the A finished? No. Again, this A can be added back to ready queue. Then B is the first process in the ready queue, which can start its execution up to 4. By 4, who is coming? C is coming. And with this execution, is the B is over? No. Again, B can be added back to ready queue. Then A is the first process, going to get executed up to what? Up to 5. Because A execution time is total 3 units. Out of 3 units, already 2 units it is executed here, 1 unit it is executed. So A is finished now. Okay. And by 5 is anybody is coming? No. And that too, no need of adding this A back to ready queue because its execution is over. Then what is the first process? C. Going to get executed up to 7. So by 7, who is coming? D is coming. So add the D. And is the C is finished with this execution? No. Again, this C can be added back to ready queue. Then B is the first process, going to get executed up to 9. And with this execution, is the B is finished? No. But who is coming? E is coming. Right? And with this execution, is B is finished? Not yet finished. Again, this B can be added back to ready queue. Then D is the first process, going to get executed up to 11. And with this execution, is the D is finished? No. Again, this D can be added back to ready queue. Then C is the first process, going to get executed up to 13. And with this execution, C is finished or not? Yes. No need of adding this C back to ready queue. Then what is the first process that I am having here? E. So now he can start execution up to 15. And with this execution, E is finished? Yes. No need of adding this E back to ready queue. Then what is the first process I am having? B. Going to get executed what? Up to 17. And with this execution, right, with this execution, B is finished. So B total, how many times it is executed? 1, 2 and now 3, right? So total B is also finished. No need of adding this B back to ready queue. Then D is the first process, going to get executed up to what? 19. Because D total execution time is 5, out of which already 2 units it is executed here. Now one more 2 units it is executed. And with this execution, D is not finished. Again, D can be added back to ready queue. Now D can start its execution again up to 20. So with this execution, all processes are finished. No need of adding this D back to ready queue. Then completion time of every process, if you take, A is finished at what time? 5. B is finished at what time? 17. C is finished at what time? 13. Okay. D is finished at what time? 20. And E is finished at what time? 15. So this is the execution time of, completion time of all process in the context of round robin. Then turnaround time. Completion time minus arrival time. 5. 17 minus 2. 15. 13 minus 4. 9. 20 minus 6. 14. 15 minus 8. 7. Then waiting time. 5 minus 3. 2. 15 minus 6. 9. 9 minus 4. 5. 14 minus 5. 14 minus 5, how much? 9, and 7 minus 2, 5. So this is the waiting time of every process. Okay. Then, so 10 minus 2, so here I have to 7 minus 2, 5, 14 minus 5, 9, 9 minus 4, 5, 15 minus 6, 9, 5 minus 3, 2. Yes, perfect. So then, if you verify this average waiting time here, how much it is coming to? 5 plus 5, 10, and this is 20, right? 18 plus 2, 20, and 10, so total 30. So with respect to round robin, you are getting how much average waiting time? 30. Okay, average waiting time in the context of round robin, 30 by 5. Then how much you are getting? 6. Okay. So then the question is asking about average waiting time that is deferred. How much is deferred? So I can say 6 minus 0 and 4 minus 6. If we can see, we are getting 1.4. So 1.4 is the answer for this question. But the motive is this is what concept of your FCFS and round robin. Okay. Verify, I mean, whether I committed any calculation mistakes or not, but I hope so I have done properly. But this is what the basic concept of round robin and FCFS. Okay, right. So this is what average waiting time in the context of FCFS. This is what average waiting time in the context of round robin. So average, the question is speaking about differing, so that this is what the difference, 1.4. Okay, right. So let's move to the next question. Yeah, so look at this question. Consider 3 processes, all are arriving at time t0. Total execution time of every process is like 10, 20 and 30 respectively. Each process spends first 20% of execution time doing IO, then the next 70% of time doing IO, right? First CPU and then IO, and the last 10% again doing with CPU. So we are executing FCFS here, and the question is asking about percentage of time, percentage of idle time, right? CPU idle time, and multiple processes can perform their IO operations in parallel. According to this line, multiple processes can perform their IO operations in parallel. Okay, so let's see the Gantt chart for this question. So all processes arrived at the same time, that is 0. Okay, so P1 is arrived, P2 is arrived, and P3 is also arrived. And this is the IO device 1, this is IO device 2, this is IO device 3, and each IO device is having its own device queue. So first 20% doing with the CPU means no process is going on to IO. So every process is starting the first 20% of their execution with CPU. It means first P1 will start its execution up to 2, because its total execution time is 10. Out of 10, 20% in the sense 2. That's why 2, and then it is leaving to IO. So from 0 to 2, this IO device 1 is sitting idle. Then who came? P1. So how long it is going to spend its execution on the IO? 70 units. Out of 10, 70 units in the sense 7 units, means up to 9 this P1 can be with IO. While this P1 is performing IO operations, by that time P2 and P3 are in the ready queue. Then among these two, who will go? P2 will go, because lowest process ID. So P2, 20% of 20, what is that? 4. So now it is going to execute up to 6, and then it is leaving to IO. So from 0 to 4, this IO device 2 is sitting idle. Then P2, 0 to 6, you can say 0 to 6, it is sitting idle. and then at 6 it is starting its IO operations. What is the length of IO operations? Out of 20, 70%, in the sense 14, means up to 20 it is going to get executed here. In the meanwhile, by 6 only P3 is available. Now P3 will go on to the CPU. Going to get executed up to how much time? 20% of 30. What is the 20% of 30? What is that? So you can say, 10% of 10% of 10% of 10. What is that? 1, right? So what is my question here? 20%. First 20% is with 30. Okay. So then it is coming to what? How much? If you consider out of 20, with 20% of 10 in the sense 2. 20% of 20 in the sense what? 4. Then 20% of 30 in the sense what? 20% of 30, if you consider, it is coming to how much? Please verify. 20% of 30. It is coming to 6, right? So what does it mean? 6 units it is going to get executed here on the CPU, right? So by this movement, who is coming? P1 is coming back. So now P1 is coming. By 9 itself, P1 is coming, and then P1 will, now it can leave to IO. Now it can leave to IO. On the other hand, from 0 to 12, this is sitting idle. Then P3 will start its IO operations, right? So 20% of total execution time is this one. So 70% of 30 now for P3. 70% of 30. So 70% of 30. You can say it is 21. So it is going to execute up to what? 19, correct? So 70% of 30 is 21. So means up to 33 it is going to get executed here. Okay, P3 is going to get executed up to 30. On the other hand, this P1 is available. P1 is going to perform last 10% of its CPU. So 10% of the CPU is what? 1, right? So 10% of 10 is 1, right? It is going to get executed up to 13. See, please look into this. So if you, this is P1, this is P2, this is P3. Okay, let me draw the system carefully. So PID, P1, P2 and P3. Arrival time I just considering 0, 0, 0, and execution time first CPU and then IO and then CPU. So if you consider first 20% of P1 is 2, 20% of P2 which is 20, it is 4, and this is 20% of 3 which is 6. Then 70% it is 7, it is 14 and it is 21. And this is going to be 1, 2 and 3. 10% of again. So this is the way how it is being splitted. So for P1, 2 units it is executed here, then 7 units it is executed here, and then it is came back at 9, then it is performing its IO operations. So now P1 is finished here. Now P2 up to 4 means 2 to 4 it is got executed, means 4 units of CPU is over, then 14 units of IO operations are in progress. By the time P3, 6 units it is got executed here, and then it is went to the IO and it is performing its IO operations up to 33. So by 13 nobody is coming, it means up to 20 it has to sit idle. Then by 20 who is coming? P2. So P2, 14 units IO operations are over, remaining 2 units now it wants to perform. Up to 22 it is going to get executed. Then at what time this P3 is again coming back? At 33. So up to 33 the CPU should sit idle. At 33 P3 is coming, then P3 is going to execute up to 36. So the total time the CPU is spending here up to 36 in order to execute all these processes. The question is asking about how much idle time, percentage of how much idle time, percentage idle time, right? Idleness of the CPU. How much percentage of idleness is there of the CPU? So here 7 units is there, plus here 22 and 33, 11. So total you can say 18 by 36, which is 50% of time the CPU is sitting idle here. 50% of time the CPU is idle here. So if you verify here, 2 plus 1, 3, 3 plus 4, 7, 7 plus 2, 9, 9 plus 6, 15, 15 plus 3, 18, correct, 18, and then here I am having 7 units and here I am having 11 units, so total 36, so 50% is the idleness here. Idleness of the CPU in this context is 50%. Okay, so this is what the answer for this question. Let's move to the next question. So this is the next question that we are having. The question is asking about at what time J3 is able to finish its second instance. Second instance of J3, by what time it gets finished? So J1, J2, J3 if you take, the question is clearly mentioned at first millisecond. It means all are arrived at 0 itself, and J1 is again can appear in the ready queue at every 3 milliseconds or else at every 3 units. So means after 0, second instance of J1 can be at 3, third instance can be 6, fourth instance can be at 9, then fifth instance can be at 12, then 15, and then 18, and then 21. So like this it goes infinite number of times. Then J2, first instance is at 0 and second instance is at 7, then 14 and then 21, like this it go up to infinite number of times. Then J3, first instance is at 0, second instance can be at 20 and then 40, so like this it goes up to infinity. Infinite number of times the process can appear into the ready queue. That is what the meaning of this line. Infinite sequence of jobs. Okay. Now, every time they are appearing into the ready queue, they can able to execute 1 unit, 2 units and 4 units of time. J1 is able to execute every time its presence in the ready queue, it is able to execute for 1 unit. J2 is able to execute for 2 units, J3 is able to execute 4 units on the CPU. Now, if you draw the Gantt chart for this system, so we can draw the Gantt chart like this. At 0, all the tasks are there, means you can say all the jobs are there. J1 is there, J2 is there, and J3 is also there. But which one is having high priority? If you check, the question is clearly mentioned, priorities are inversely to their periods. What does it mean? whichever process is arriving in a shorter amount of time into the ready queue, that process can have high priority, which means J1 is appearing into the ready queue for every 3 units, J2 is appearing for every 7 units, J3 is appearing for every 20 units. So which one is appearing in a shorter amount of time period repeatedly into the ready queue? J1, which is having high priority. So that's why first J1 will start its execution up to 1. By this movement J2 and J3 is there, then J2 will go up to 3, because every time they can able to execute 1 unit, 2 units and 4 units. Then by 3 J3 is there and J1 is also arriving. Which is having high priority? J1. So J1 will go up to 4. Then by 4 we are having only J3. So now J3 will go on to the CPU, up to 6 it gets executed, but by this 6 who is coming? J1 is coming. Now J1 will go up to 7. By 7 J3 is there, but along with J3 who is coming? J2 is also there, because second instance of J2 is happening. Then J2 will go up to 9, it gets executed. By 9 who is coming? Again J1 is coming. So now J1 will go up to 10. So by 10 nobody is there in the ready queue. So that J3 will go on to the CPU. J3 can be executed up to 12. So this is the first instance of J3 gets finished. By 12 who is there? Only J1 is there. So now J1 will go on to the CPU up to 13. Then by 13 nobody is there in the ready queue. Up to 14 the CPU is sitting idle. So by 14 who is coming? J2 is coming. So now J2 will go on to the CPU. J2 is going to get executed up to 15. But by 15, while J2 is in execution, J1 is coming, so that J1 will go on to the CPU because J1 is having high priority. Up to 16 it gets executed. By 16 you have J2. J2 is going to get executed now up to 17. By 17 nobody is coming into the ready queue, and it is going to sit idle up to 18. By 18 J1 again will come. Now J1 will start its execution up to 19. Okay. By 19 nobody is coming, means it is sitting idle up to 20. By 20 who is coming? J3 is coming. Now J3's second instance is going to start its execution up to what? 21. But by 21 who is coming? J2 is coming as well as J1 is also coming, right? Then J1 will go on to the CPU, gets executed up to 22. Then you can have J3 and J2. Now J2 will go, gets executed up to 24. Then J3 and J1 can be there. Then J1 will go on to the CPU, gets executed up to 25. But by 25 nobody is coming, so that only J3 is there. J3 it is going to get executed up to 27. Okay, 27. But by 27 who is coming? J1 is coming. Now J1 will start its execution. So 27, J1 will start its execution up to 28. Okay, up to 28. By 28, by 27, J3 only there. Now J3 and J2 will be there now by 28, because 28, the fifth instance of J2 can occur. So now J2 will go up to what? 30. By 30, J3 is there and J1 is again will come. So now J1 will go up to 31. Now only J3 process is there, so we can hand over this J3 and it will get executed up to 32. So this is what the completion time, the second instance of J3 is finished. Second instance of J3 is finished. Then the question is asking about idle time. How many units of idle time is there? If you check here, 1 unit of idle time is there. Here 1 unit of idle time is there. Here 1 unit of idle time is there. Correct? So total 3 units the CPU is sitting idle. So overall I can say 3 is the answer for this question. Okay? 3 is the answer for this question. Next, coming to next question. So check this question, how many times that A's can be printed? So first if you start with the P0 parent process, it is calling this fork, then this is P0 is creating P1 child process, and you know fork is returning 0 to the child process and positive value to the parent. But for 1 and 0 this condition is true, then both P1 and P0 can enter into if condition, if clause. Then both are printing this A for A's for 2 times. Then both P0 and P1 are executing this if clause again. Now P0 is creating P2 and P1 is creating P3. So now P2 and P3, these two are having PID, which is a child process ID 0, and these two are having 1. Right? For all these processes, this particular if clause condition is true and all the process can enter into if clause. Then all these 4 processes can execute this printf means 4 times. So nobody is entering into else and all 4 processes will come to this printf, and here all 4 processes can able to print this A's for 4 times. So overall how many times that A's is got printed? Here 2, here 4 and here 4. Total 10 times that A's is got printed. So 10 times is the answer for this question. Okay, 10 times is the answer for this question. Then coming to next question. This is based on deadlock. A system contains 3 programs. So number of processes is 3 and each require 3 tape drives. Demand of every process is 3, which means you know that there is a condition we have, demand of all process is less than number of resources plus number of processes. So 3 processes and each one is having 3 demands, so which means 9 is the demand, is less than, we need to find out number of resources plus 3, number of processes is 3, so that 6 is less than m, or you can say m is greater than 6. M greater than 6, what are the values that you are having? 5, 4, 3, 2 and 1. The question is asking about maximum number of tape drives. Among these, what is the maximum? If you can see 5. So 5 is the maximum value of m for which the system, right? So maximum value of m for which the system can enter into deadlock, right? So the question is asking that the maximum number of tape drives the system must have such that you can say this is what the maximum value of m, the system will not occur into enter into the system, correct? So verify 9 is less than m plus 3, so 6 is less than m, less than m, 6 is less than m. Then what are the values that I can have for m, or else I can also write m is greater than 6, m is greater than 6 in the sense I can have 7, 8, 9 and etc., correct? 7, 8, 9, 10 and so on. Then among these minimum value is, you can say this one. This is the minimum value for which the system will not enter into the deadlock, and this is the maximum value for which the system can enter into the deadlock. So that's why 6 is the answer for this question. Okay. So 6 is leading to the deadlock, but 7 is the minimum value for which the system will not enter into the deadlock. So 6 is the answer for this question. Next, this is also based on deadlock concept. Maximum demand is this, so that need we need to calculate 7 minus 2 5, 6 minus 1 5, 5 minus 2 3, 4 minus 1 3, and available I need to find out what is available. Total 9 drives are there, 9 resources, and among them which are being allocated 6, so that I am having 3. So now first, which process can start its execution, either P3 or P4. So for example, if I start with the P3. P3 need is less than equals to available. Yes, P3 also can be finished. I mean P4 also can be finished. Yes, this is a possible safe sequence, right? This is possible. Then P4 if you take, first P4, yeah. So first P4 if you take, need is less than equals to available. What is the need? 3. 3 is less than equals to 3, condition true. So that work is equals to work plus allocation. What is the work? 3 plus what is allocation of P4? 1. So that 4. So after P4 is finished, am I able to satisfy? Am I able to satisfy P1? P1 need is 5. I cannot satisfy. And P2? I cannot satisfy. So that the question is asking, which of the following is not be a safe sequence? Not be a safe sequence. So this is a possible safe sequence, but the after P4 I cannot satisfy, because after P4 is finished, this is what available. With that available, the need of P1, the need of P2 cannot be satisfied. So that all these are all not possible safe sequences. Only D is the possible safe sequences. So that option is option A, B and C is the answer for this question. Okay. So which are the following sequences? It is a MSQ kind of question. So ABC is the answer for this question. So like this we are having several questions and we can discuss so many questions with respect to operating system, right? I hope the session is benefited to you. Okay. Thank you so much. All the best for your revision process. Have a great day. Good night.